Hi, I am Marc Girondot, and I have produced a software named BoneProfileR in collaboration with Jordan Gônet and Michel Laurin to help researchers to analyze bone section. I have made this little video to explain in more details than what we have done in publication, some particularities of this method and the software. So, bone is a typical structure in most vertebrate animals, and the bone function can be very diverse. It permits to protect various organs of the body. It produces red and white blood cells. It permits to store mineral, provide structure and support for the body, and enable mobility. Bones comes in a variety of shape and size and have complex internal and external structure. I have taken these definitions from Wikipedia. Then bone structure and ultrastructure can be used to get information in relation to the above structures. A bone section is generally more or less round shape and is composed of non-mineralized tissue surrounded by mineralized tissue. The mineral at the periphery of the bone is generally dense and is named cortex, but the distribution of mineralized tissue can be very diverse. The structural diversity has been described in an entire body of literature, and with only slight exaggeration, every bone has a name describing it. This is the reason why we need a model. If we stay at this level, each bone being particular, it prevents any generalization about the pattern and processes that have generated this diversity. The use of a model to describe repartition of mineralized tissue permits to synthesize multidimensional complexity of an object into a smaller number of dimensions, allow reproducible analysis to be done, and permit quantitative comparison. Just at this point, it is always good to remember that this is a model, and as George Box said in 1978, all models are wrong, but some are useful. And I hope that BoneProfileR is a useful model to describe diversity of mineralization of bone sections. If you look at this bone section at the top, we need a quantitative model that goes from 0, non-mineralized center, to 1, mineralized periphery. However, some bones have a mineralized center, so the model should accommodate that center capacity could be higher than 0. And some bones have a very, very thin cortex, and the model should accommodate that periphery capacity could be, in average, lower than 1. For this reason, we used a scale logistic model. The logistic equation produces values constrained to be between 0 and 1 with 2 parameters that have biological interpretation. In this equation, P is the distance to the center, from 0 the center to 1 the periphery, where the theoretical capacity is 0.5. And S is the slope of capacity change at distance center equal P. This equation produces value from 0 to 1, but we have seen that we should accommodate with a mineralized center or poorly mineralized periphery. Then we use a scaled logistic model with the equation at the bottom. So we have now 4 parameters S, P, max, and min. However, there is still one problem. The logistic equation has a big constraint. It is symmetrical below and above P. However, there are no reason to force the complexity change to be symmetrical. Thus, we have developed a new function with similar characteristic than the logistic equation, but allowing to develop a asymmetrical pattern back below and above p value. This is the Flexit equation. The Flexit equation has very similar characteristic than the logistic equation, just it can be asymmetrical. Then we can ask, should we choose between logistic or Flexit? We can use the model selection using HelpersMG information criterion to do this. But I don't think it's a good idea because logistic equation force symmetrical pattern and there is no reason to think there is a symmetrical pattern. So I don't think it's a good idea to make selection model between logistic and Flexit. We should use always Flexit to be able to describe the diversity of pattern. Anyway, if you choose to do model selection, at the end, you will always choose Flexit based on the 100 section we have analyzed until now. Another problem is where is the center of the section. It is easy to estimate where is the center of the section or where is the center of the non-mineralized tissue. If both the center are at the same position, we can use this center. But if they are not at the same position, it means that the growth of the bone or the resorption of mineral was not isotropic, not the same rate in all the directions. In such a situation, which is the most typical situation, we developed the concept of ontogenic center, which is the center of the bone before any anisotropic change occurs. Generally, you should use ontogenic center for your section. The adjustment of the model is done by splitting the section in small portions. We cut the section from the center to the periphery by 100 little portions and turning around the circle by 60 slices by default, but it can be changed, but 60 generally good compromise between quality of information and number of analyses to be done. So for each section, we count how many pixels are mineralized, how many pixels are non-mineralized, and such a variable follow a binomial distribution. So it is easy to estimate the likelihood of the compactness in each of these sections. So this is the model. And the observation of number of mineralized and non-mineralized pixels are the data. So we have data, we have model, and we try to make the best correspondence between data and model. We will see a little bit later how mathematically we will do. Now let's run an analysis. You can use or the simplified online version on BoneProfileR version 4, located at this URL. You can make a pause on the video to get the link using this QR code. It will be simpler. An alternative is to install the full BoneProfileR software on Air, and it will allow you to use all the functionality of the method. Air is known for being difficult to access. That's true. I cannot say something else. But honestly, it's worth the effort. You will see that with Air, you can do many different things. And the intellectual and time investment is really worth it. So first, you must install Air and Air Studio. Air is both a software and a language. Air Studio is a graphic user interface. So when you use Air Studio, the true work is done by Air. Air Studio is just graphic user interface. This is very useful, but if you publish results, you must give the version of Air, not really the version of Air Studio, which is just graphic user interface. Now that you have Air and Air Studio, you must install the BoneProfileR package developed by myself with the help of Michel, Laurin, and Jordan Gônet as tester. Most recent versions of BoneProfileR and HelpersMG package are located at this URL. These codes are in the description of this video. And now let's try our first analysis in Air. The code is available within Air with the help BoneProfileR help. It will generate this help and you can just make copy and paste. First, you must load the package with the library BoneProfileR. Then you will use the stored image in the package with this command. This is an hedgehog bone section. And with this command, you get the location of this bone section within the package. We open the image. You can open image as PNG, as tiff, as JPEG. I do not recommend JPEG. JPEG is a format of image that you lost quality when you use JPEG. It's better to use tiff, for example, or PNG. When you have loaded the image, you can plot the image with this function, plot bone. We have stored the image in the object bone and type original. We just plot what is the image. Here, this is green and white. White is a mineralized part of the section. Then we use automatic identification of background and foreground using the function BP detect background and BP detect foreground. And here there is something important. We introduce the analysis name. I use for BoneProfileR software that stores the analysis with the image. In many Air software, you have the original object, your data, and you have many files with all the analysis. Sometimes you can be lost. I decided to use a system where the analysis is stored within the image. And you must give a name. Here I give the name logistic. It is just a name. You can use any name. And I store the result in the logistic analysis name. So I detect background. It is correctly detected. It is green background. Perfect. I detect foreground. It detects white foreground. Perfect. And I detect the center. You have several methods to detect the center. Generally, the accurate method is very good. You have also fast method, but if your computer is very slow, the fast method can be used, but generally the accurate method is what you should use. You can anyway use help with the name of the function, and you will see other options. So now we have read the image, we have detect the background, foreground, and the center, and we should estimate compactness with the function bp estimate compactness using the analysis logistic, which is the analysis what we are working for, and we will use the ontogenic center as I described previously. Never forget to check that all is okay. Using plot type mineralized, you will see the top image, and you will see that the bone is correctly analyzed and interpreted. And with plot bone type observation, you will see in a black curve the distribution of compacity from the center to the periphery of the section, and the blue line represents the number of pixels for each section of the bone. And you see that obviously at the center you have less number of pixels than at the periphery. We should take into account this to not make biased estimation, but the software will do this for you. Now that we have the observed compactness, which is data, we should fit the model, which is the aim in the previous slide. First, we fit logistic model, the simplest model with BP FitML compactness. This is in the analysis logistic, as we don't put any parameters. By default, it will use a logistic model, which is a scaled logistic model, which is a simpler one. But we will not stay here. Immediately, we will fit a flexit model, which is, in my point of view, the model that you should fit, and you should work with this flexit model. So with the first command, we take the parameters values that have been fitted for logistic model. We duplicate the analysis logistic to analysis flexit, and we fit a new flexit model. We add the parameter K1 and K2 to the parameter fitted for logistic, and it will give you a flexit model. We have now a model fitted by maximum likelihood. And we must stop a little bit about what is maximum likelihood and is it what you. There are two main statistical methodologies that can be used to fit the parameters. This is maximum likelihood or Bayesian statistics. We can say there is another one, least square statistics for proportion. It is wrong, it is biased. Never use least square statistics. It is not proposed in the software anyway. The choice between maximum likelihood or Bayesian is not a matter of personal choice or to be a la mode with Bayesian statistics more complicated. The maximum likelihood is based on searching for the model M, maximizing likelihood of data according to the model. Model selection is based on an archaic information criterion using also the likelihood of data according to the model. The problem is that we don't know the model, and then the use of data knowing the model is misleading. We know the data and we search for the model, not the reverse. So we are interested in the likelihood of the model knowing the data. Bayesian statistics offers this latter perspective, the likelihood of the model knowing the data. Model selection in Bayesian world should use Watanabe archaic information criterion and not IC. So I will continue to use only Bayesian statistics because it has many advantages over maximum likelihood, and this is really what you search for. We can fit a Bayesian version of this model using this command, using the function BoneProfileR fit Bayesian compactness. When you use Bayesian analysis, you need a prior. A prior, this is what information you have on your parameters before the analysis. If you consider you don't have information, just use uniform density. This is what is done by default here. You can use other priors, but by default here I use uniform because generally we don't know much about PS, min, max, key 1 and key 2. In this analysis, you need to give some information about how it will do the Bayesian analysis. For example, nAdapt is a part of the analysis where it begins to adapt the model, and then after it will run the model during n iteration, here 10,000. Thin is also an important parameter because it permits to remove autocorrelation. Thin 10 is generally good choice. N-chain is if you want to run several analyses in parallel. Generally, I use one, but for some situation, it's better to use higher dimension of number of chain. Adaptative is during the search of the model, it tries to make the model more efficient. Generally, what you should take into account is more nAdapt and niter, number of adaptation before to run the true analysis and number of iteration, the true analysis. Here I use 1,000 adaptation. When you have done the analysis, always check with this command if you have correct results. Normally, if the analysis is correct, it should be more or less flat. You have big fluctuations, but you will not have tendency, or you will not have big drops and up of the or likelihood for the first graph or the values parameters for the bottom graph. Here you see that the likelihood at the beginning was not very stable. It drops, then it goes up, and after only it stabilizes. And at the bottom, this is the S parameter. You see that at the beginning, it does not look like after the analysis. Here, the adaptation was too short. We run again the analysis with adaptation of 10,000 iteration. And now you see it is more homogeneous. It is more, you don't see big drop and falls, and the same for the parameters. So 10,000 adaptation is generally good compromise. Now you can check the Bayesian fitted model with MCMC uncertainty with this function, and you plot, you see the observed compacity in black lines, and the model is the curve that is shown more gradual curve, and you see that the credibility interval, which is how you know the model, the credibility interval is very thin. You know relatively well the model. With this function, you can have the fitted values, their average, the standard error for each parameter, and the quantile for each parameter. K1 and K2 are more difficult to interpret because the logistic symmetrical model is observed for key equal 1. So when you look at the key 1, if you look the quantiles are negative for lower and median quantiles and positive for the higher quantile, but still less than 1. So the key 1 is really different from a logistic model. The key 2, you see, is always positive, but it goes just at the limit of 1. So it is also different from a logistic model, but not so different. If you look at the curve, you see indeed that it goes from the low compacity at the center to high density at the periphery with an asymmetrical model. It goes faster at the beginning than at the end. The Flexit model permits this. Logistic will never allow you to fit such a model. You have two ways to analyze the compacity of a bone. The compacity of a bone can be simply the number of mineralized pixels versus non-mineralized pixels. This is the compacity of the bone. The linearized compacity is the integration under the curve. This is the compacity with compensation taking into account that the number of pixels at the center is lower than at the periphery. You can have this information using summary. Here, summary bone and the analysis Flexit. You have the global compactness is 0.667. The linearized compactness using maximum likelihood or MCMC are very similar, and it describes the integration under the curve. What you should use when you are doing analysis, I think that both are interesting. The observed global compactness is something very close to the observation, And the linearized compactness is something that integrates the model, the distribution of compacity along the gradient from center to the periphery. So both values are interesting. They do not give you the same information. What else? The software permits also to analyze partial section. Then for partial section, you cannot use the automatic center detection. You must choose by yourself where is the center. You can make a radial pattern of compacity or a periodic compacity, which is a new model that I developed for version 4 of BoneProfileR. And I will explain this in more details in the next video. Thanks for your interest.